Continuity. Up to this point, you probably have just talked very vaguely about what it means for a function to be continuous, but what we're going to do today is learn the formal mathematical definition of continuity, and then we're going to be able to identify points of discontinuity graphically and algebraically, meaning looking at them on a graph and by looking at just their equations. And we're also going to be able to identify the difference between two different kinds of discontinuities. That's removable and non-removable. So first of all, what you probably have learned about continuity up to this point is just a very informal definition. The fact that you can draw it without lifting your pencil. So all five of those shapes I drew are continuous. And that's really not a bad definition as far as informal definitions go. It gives you a really good idea of what the idea behind it would be. But now that we're in calculus, we can know the formal definition. And the reason they waited all the way till now to tell you is because the formal definition includes limits. So up to this point you didn't know limits, so you couldn't have done this. So what we're going to do is kind of try to discover what the formal definition is. And we're going to do that by showing what continuity is not. So if you look at this first picture on the left, the function is clearly not continuous at point C because there's a hole. But try to think about what that really means mathematically. If we have a hole, then that means that the function does not exist at point C. So f of c does not exist. So we know if the function doesn't exist, we can't be continuous. So now let's try the next one, the middle one. Okay, well if you look, the function does exist here, right there at that spot I drew in blue, but we're still not continuous. So apparently the function existing really isn't enough. That's not going to be sufficient. Because the function exists, but we're not continuous, and this time it's because the limit does not exist. Because we were approaching 2 from this side, and we're approaching 1 from this side. On this middle one again, the function does exist, but the limit doesn't, because we approach different things from each side. So we have to say the limit as x approaches c of f of x does not exist. So far we know if the function doesn't exist, we're not continuous. If the limit doesn't exist, we're not continuous. So let's see if we can figure out what the problem is on this very last picture, the one on the right. Because if you look, the function does exist. We've got a point right there. Also, the limit exists. We're approaching the exact same value from both directions. So what's the problem this time? The function exists, the limit exists, but we're still not continuous. Well, the reason we're not continuous on this last one is because even though the function exists and the limit exists, the function and the limit aren't equal to each other. In this case, the function is equal to 1 and the limit is equal to 2. So we run into a problem when the limit at a point is not equal to the function at that point. So now we know what causes things to be discontinuous, and just by flipping those to the positive, we can find out the requirements for something to be continuous. So continuity at a point. A function f is continuous at point C if the following three conditions are met. First of all, the function must exist at point C. Second, the limit must exist at point C. And third, the function value must equal the limit at point C. If you're in my course, you do need to have this list memorized. This will be a question on your test and is important for the AP test as well. You can know it in this format that's kind of English based, or if you want, I'm going to write out also kind of the math way to say this. For the function existing, you would say f of c is defined or exists. You could say exists as well. That would be okay. Number 2, you would say the limit as x approaches c of f of x exists. And finally, that the function value must be equal to the limit at that same point. So whether you want to memorize the black things that's typed out, that's kind of just the English way of saying it, or you want to memorize the blue that I just wrote, that's the more math way to communicate it. Either way is fine. The point is that you understand these three requirements. Now we want to talk about the different types of discontinuities. First of all, there is a removable discontinuity, and that's a hole. There's also non-removable discontinuities, jumps and vertical asymptotes. The key here is a removable discontinuity can be fixed with just a single point. If you just put one single point in that hole, you fix the problem. But with a jump or vertical asymptote, one point cannot bridge that gap. It's not going to work. That's why they're called removable and non-removable. So if we look here, we've got some examples where I want you just to be able to look at the equation and determine if it has a removable or non-removable discontinuity and where. Well, I'll go ahead and tell you, it turns out to be real simple to figure out the difference between the two. If you can cancel it out, it's removable. If you can't, it's non-removable. And you'll see what I mean in just a moment. So let's look at the first example. F of x equals 1 over x. This is going to have a discontinuity at x equals 0. And hopefully you would have known that already because we don't exist at 0 because that would put a 0 in the denominator. And this one is non-removable. Non-removable because you can't cancel out that x. You'll see in a moment what it means when we can cancel it out. But we can't cancel that x out from an x on top, so this is non-removable. Specifically, it's going to be a vertical asymptote. We'll talk more about asymptotes a little later. Okay, next example, we know there's going to be a problem at x equals 1. That's going to be some kind of discontinuity. The question is, what kind? Well, if you look, you can factor the top into x plus 1, x minus 1, which then allows you to cancel out the bottom. So this is a removable discontinuity, which means it would be a hole. So that's what I mean by cancel it out. If you can cancel out the term that causes the problem, then it is a removable discontinuity. So then in the third example, we have discontinuities at both -4 because of this term and at +5 because of this term. Well, if you notice, x plus 4 will cancel out with something on top. That tells us it's a hole and it's removable. However, x minus 5 won't cancel out, so x equals 5 is non-removable. Again, it would be a vertical asymptote. So I have a few more to look at. We have f of x equals the absolute value of x minus 2 over x minus 2. Okay, the problem is going to be at x equals 2 because it there we go. If we plug 2 in, you get 0 in the denominator. You can't divide by 0, so that's why it's a discontinuity. And this is actually a non-removable kind. Because of the absolute value on top, we cannot cancel out those x minus 2's. You cannot cancel out something in absolute value with something that is outside of absolute value. And this is actually a jump. Absolute values are going to create a jump. Okay, this next one is called a step function. It's specifically the greatest integer function. It looks something like this. So if you look, it has lots of discontinuities. And if you look closely, it has discontinuities at every single integer. So on the in-between, you're okay. Those horizontal parts, they're fine. There's no discontinuities in them. But when they jump, they always jump at the integers. So we would say that this has non-removable discontinuities at all integers. And the shorthand way of writing integers is just that funky looking z. It's basically a z with two backs. Okay, and last one we're going to look at is a piecewise function. For a piecewise function, you need to first look at the individual functions and see if they have any problems. So think about x plus 1. It doesn't have any issues. There's no denominator, so it's not going to have any discontinuities by itself. Same with x squared plus 1. Individually, they're not a problem. But since it's a piecewise function, we have to look and see what happens where they meet. And we know, because of this number over here, that it meets at x equals 0. So to figure out if we have a discontinuity there or not, just plug 0 in. If I plug 0 in here, I get 1. If I plug 0 in here, I also get 1. So that tells me they actually meet at the point 0, 1, in which case there is no discontinuity. So we would just say this is continuous on all real numbers. But there will be times with piecewise functions where when you plug in that number, it's going to give you different results. And when that happens, you would say you have a non-removable discontinuity at whatever this x value is over here that you plugged in.